For almost a decade, it really felt like we had this quiet, settled understanding of the desktop, right?
Oh, absolutely. It was sort of relegated to the background.
Yeah, just a utility device. We thought the world had, moved on to smartphones, or maybe we just settled into this predictable cost equilibrium between our devices.
Right, a stable, boring piece.
But let's ask the question right now, because it feels urgent. Is the desktop war truly over?
No.
Or did the sudden arrival of AI just throw a massive wrench into that whole equilibrium?
It absolutely shattered it. And what's really fascinating here is how AI, almost overnight, has completely renewed the competitive landscape.
It feels like the stakes are higher than ever.
They are. For the first time in, what, decades?
Mm-hmm.
Microsoft can't just rely on the sheer ubiquity of Windows anymore.
It's not a guaranteed win.
Not at all. They are having to fight hard architecturally, strategically, just to keep the modern AI developer on their platform.
And it's not just Windows feeling the heat. For years, Apple had its fortress, right? The essential machine for designers for the whole creative class.
The designer edge.
Exactly. But that edge, that aesthetic monopoly, it's starting to look a little soft now that raw compute power is what really matters.
Precisely. The goalposts have completely shifted from aesthetics to deep, hardcore architecture.
And maybe the biggest story here, the most inspiring comeback, is the platform most people just forgot about, Linux.
Yes. Linux, after completely capturing the data centers, the entire cloud backbone of our world, is back in the desktop game.
And it's challenging both Windows and Mac, not with some old ideology, but with sheer technical genius.
Genius technical breakthroughs and, well, a bit of compromise. A necessary compromise on that old, staunch FOSS philosophy.
Right. This isn't the Linux from 10 years ago that was, impossible to use unless you were a kernel engineer.
No, this is a modern, pragmatic Linux. And when we talk about that, we have to talk about Ubuntu, the practical challenger leading the charge.
And you can't mention Ubuntu without paying respect to its mothership.
The grand old purist. The one and only Debian.
This whole shift is just... it's inspiring. You see developers everywhere betting their careers, their savings, their future on this AI dream.
And the platform they choose right now defines everything.
Okay, so listen up, because we have to give a sincere caution right at the start of this deep dive.
We do.
We are going to get exceptionally technical. We are diving deep, right into the very core of some heavy computer science debates.
Yeah, we're talking kernel drivers, synchronization protocols, RASCV coprocessors, memory management units.
This is the stuff that separates a hobbyist machine from a serious AI workstation.
For sure.
It sounds like a lot of jargon, but we promise we're here to be your guides. We will do our absolute best to make this an easy, engaging listen.
Even if your daily driver is a Chrome OS machine.
Which is a totally valid choice. If your goal is just browsing or email, they're fantastic value. We love them for their cost, speed, battery life.
All the things a great consumer machine needs. But if your goal isn't just consumption, if your goal is serious development, heavy AI training,
then the choice you make right now, that architectural choice, it defines your ceiling.
It determines whether you can even load the big models or if you just hit a wall instantly.
So pay attention. The technical details matter, and we're going to translate them into what they mean for you.
Our scope today is a deep, deep dive into the architectural choices defining the modern AI desktop.
We're comparing Windows, Ubuntu, the purist Debian, and of course the completely separate world of Apple Silicon. We're going to see how each one handles NVIDIA's hardware.
And how each one manages the single biggest constraint of the entire AI era: memory, capacity versus velocity.
And this mission today, it builds directly on our last deep dive, where we talked about modern portfolio theory versus the Bubblehead's 40.6 easy strategy.
We'll put the link in the description, of course. The whole idea there was, how to get a window of financial independence, maybe 10 years.
The freedom to just focus on deep development work at that intersection of, say, AI and decentralized tech.
Exactly. So our goal here is laser-focused to help that budget-conscious AI developer, the one who's staked everything on this dream, make the first, most fundamental decision.
Their desktop OS.
Forget what you used in college. This is a new world, and the rules have all changed. So with all that, welcome to the deep dive. I'm Satoshi.
And I'm Satoshi. Welcome back, everyone. And seriously, we are so grateful for the amazing response, the community engagement. It just fuels this whole thing.
It really does.
And speaking of what we want to do with our own desktops as your hosts, we want to make videos of this deep technical content.
I mean, we've spent hours looking at diagrams of heterogeneous memory management and unified memory.
Yeah.
These are things you almost have to see to really get.
It's hard to communicate a page table translation with just audio.
It really is.
And, our constraint. We need to hit 1,000 subscribers to unlock the funding for the Mosaic AI video editor.
Our marketing team is obsessed. They think it's the holy grail for this kind of complex narrative video.
So all we need is your help. Please subscribe if you haven't. Share the episode in your Slack channels, your WhatsApp groups, wherever you geek out on this stuff.
Help us get visual. The world needs to see the difference between WDDM's black box and HMM's raw metal access. Trust us.
Also, please let us know in the comments if you know of a fully automated AI video editor you think is better than Mosaic. We're always looking.
You can check it out at mosaic.so. That's MOSAIC.SO.
Okay, let's get into it. The core architectural conflict. We're starting with the foundational fight. Windows versus native Linux and how they integrate with the industry standard, Nvidia.
The framing here is so important. The split is it's purely philosophical. It's strategic. It's rooted in decades of OS history.
Because the hardware is the same. An RTX 4090 is an RTX 4090, whether it's in a Windows box or an Ubuntu rig.
Exactly. The tensor cores, the RT cores, they are physically identical. But the software harness that connects that hardware to the OS, it diverges radically.
And your framing is Windows prioritizing guaranteed stability above all else.
Versus Linux prioritizing raw, unadulterated throughput. Low-level control.
Okay, so this creates two very specialized domains.
It does. Windows has really solidified its role as the client and consumer interface. Stability, compatibility, low latency for games, for Adobe.
Well, Ubuntu has aggressively become the compute and infrastructure layer.
The native language of AI training of the cloud, of the data center.
So let's start with Windows and its black box gatekeeper.
Yeah.
The Windows Display Driver Model, WDDM. This is where Microsoft puts all its stability bets.
WDDM is a monument to stability, forged in the painful fires of the early Windows era.
Right, the blue screen of death.
Exactly.
Yeah.
Its primary purpose, its original mission, was to prevent the BSOD. For a mass consumer base of billions, stability is just. It's non-negotiable.
So how does it enforce that? How does it stop one runaway process from taking down the whole machine?
It mandates a very strict bipartite architecture. It splits the driver into two parts. You have the user mode driver, the UMD, which talks to applications. And then you have the kernel mode driver, the KMD, which is the only part that can talk to the physical hardware.
And the Windows kernel sits right in the middle.
Like a mandatory, very strict traffic cop for every single hardware access. Nothing gets through without its permission.
So it's a gatekeeper, managing everything, making sure no single app can just hijack the GPU.
Precisely. And the key mechanism, the real safety net, is the timeout detection and recovery mechanism, PDR.
What does that do?
Well, let's say a developer writes a complex shader that gets stuck in an infinite loop, or some process hangs for longer than, say, 5 seconds.
Okay.
TDR immediately detects that. It sees the GPU isn't responding.
In that.
WDDM tells the KMD to just reset the entire graphics stack, kills the bad app, flushes everything, and reinitializes the GPU. The crucial part is the OS itself stays up. It never crashes.
I see where this is going. All that safety, all that abstraction from the kernel acting as a traffic cop that has to create overhead.
A huge amount of overhead. The cost is architectural abstraction. WDBM is, by design, a black box. It creates layers of indirection that actively get in the way of the low-level memory control that, say, an HPC person desperately needs.
So for an AI developer trying to move terabytes of data around, that WDDM layer is constantly getting in the way, introducing latency.
It creates a copy tax that you can never truly get rid of. Data has to be copied over that relatively slow PCIe bus from system RAM to the GPU's VRAM, and WDDM manages it all very, very strictly.
And that design, it just prevents the deepest kinds of optimization.
It does. Which brings us to Ubuntu and native Linux, where the philosophy is the exact opposite. Expose the metal, prioritize throughput.
Right.
Now, for years, the relationship between Linux and Nvidia was just friction. It was awful. Linux wanted open source purity. Nvidia had this monolithic proprietary driver blob.
A contaminant in the eyes of kernel devs.
Right. But that all changed around 2022. Not for ideological reasons, but out of sheer technical necessity.
And this was the move to open kernel modules, which was tied to a new piece of hardware, the GPU system processor, or GSP.
That's it. Nvidia open-sourced the core kernel modules because modern GPUs just became too complex to manage from the host CPU alone. Power management, security, context switching for CUDA, it was too much.
Wait, so they put a tiny computer on the GPU to manage the GPU?
That's exactly what the GSP is. A dedicated RISC-V coprocessor right on the die, running its own firmware. It offloads all that complex driver logic.
Which simplifies the driver's job inside the Linux kernel.
Drastically. And that simplification allows Linux to treat the Nvidia hardware as a first-class citizen. It enables deeper features that were impossible before.
And the most transformative of those features for AI is Heterogeneous Memory Management.
HMM is the game changer. This is what shatters that classic PCIe bottleneck, that copy tax we talked about on Windows.
Okay, so instead of slowly copying data block by block,
HMM flips the script. It
Yeah.
uses the kernel's virtual memory subsystem to sync the page tables between the CPU and the GPU.
so the GPU can just see the system's main memory directly.
It can see and access complex data structures in the host RAM transparently, as if it were its own memory. It avoids the copy tax entirely.
Wow. That's a fundamental architectural advantage. No wonder native Linux is the standard for high-end compute.
It's transformative. It's architected for maximum data velocity, which is the complete opposite of WDDM's goal of stability through abstraction.
Okay, so we've established that for raw compute, native Linux, specifically Ubuntu, has a superior architecture. But for years, the big but was always the desktop experience itself. It was just rough.
Oh, the decade-long friction over display sync was almost enough to kill the Linux desktop for good. It was so painful for users, especially with Nvidia hardware, trying to move from the old X11 system to the modern Wayland protocol.
I remember the constant flickering, the tearing, the visual artifacts. It made Linux feel incredibly unprofessional compared to a polished Windows desktop. Why was it so messy?
It was a fundamental synchronization deadlock, a clash of paradigms. The Linux graphics stack historically used something called implicit sync.
What's that?
The kernel basically just guessed the timing. It assumed that once a drawing command was issued, the GPU would finish it in a predictable time.
Yeah.
It just trusted everything would work out.
Which is fine, I guess, until you're running something demanding.
Exactly. But Nvidia drivers, mirroring their internal WDDM behavior, relied on explicit sync. They demanded a clear signal, a formal handshake, confirming that the compositor was done with a frame before they would present the next one.
So Linux was guessing, and Nvidia was demanding a confirmation signal. They were just talking past each other.
Constantly. And the result was all that visual instability that made Linux feel broken. It was maybe the single biggest barrier to entry for developers who just wanted a stable place to work.
And the sources point to a huge, but maybe underreported breakthrough that finally fixed this.
This breakthrough arrived with the Nvidia 555 series drivers. The resolution came from standardization, the Linux Sturm Sync JV1 protocol.
So they finally created the standardized handshake that Wayland and Nvidia needed to talk to each other.
That's right. And the consequence is massive. The visual instability is gone. Ubuntu 24.04 LTS now offers a flicker-free, tear-free, stable desktop experience on Wayland that genuinely rivals Windows. The user experience barrier has been eliminated.
That is a huge win.
Okay.
So that brings us to the next big choice for the AI developer, the Linux family feud. Debian versus Ubuntu.
And this is a critical choice. It's purism versus pragmatism, predictability versus agility, and it dictates your access to the latest drivers and features.
Let's start with Debian Stable, the purist. Its commitment to stability is legendary. It's the gold standard for servers.
Debian's philosophy is stable. Once a release is locked, like Debian 12, it locks driver and software versions for years. Now, they pragmatically included non-free firmware, which is a necessary evil for modern hardware to even work. But they'll stick with, say, the Nvidia 535 driver for the life of that release.
So if I buy a brand new RTX 40 series Super or a Blackwell GPU, I'm stuck with old drivers that might not support all its features.
You hit a serious feature gap. To get around that on Debian requires risky manual work, using backports or downloading raw.run files from Nvidia, which can break your system on the next kernel update.
And then there's Secure Boot, which adds another layer of complexity.
It's high friction. With Secure Boot on, you have to manually generate and enroll a machine owner key, a MOK, to sign the proprietary kernel modules. It's a whole process. If you fail, the Nvidia driver just won't load.
It's a significant administrative burden. Now, contrast that with Ubuntu.
Ubuntu is engineered for the modern hardware cadence. Their long-term support, or LTS, releases get periodic hardware enablement, or HWE, kernel updates every 6 months.
So you get the stability of an LTS base, but the agility to support new hardware.
Exactly. And the most critical piece for the AI developer is the graphics drivers PPA. It's a semi-official staging ground for the new feature branch drivers, like the 555 series.
So you get access to critical fixes, like that explicit sync we just talked about, months before they hit the main repositories.
I have to push back a little on that. If I'm running mission-critical AI, why would I risk the instability of a PPA? Doesn't that pragmatism come with a cost?
That's a great point, and it is the trade-off. Ubuntu's method introduces a small, managed risk. You're outsourcing trust. But for the AI developer, that risk is often worth it.
Because they need the cutting edge.
They need it today, not a year from now. Ubuntu lowers the barrier to entry and ensures you're not left behind by the rapid pace of GPU technology.
So Debian is for the purist, the static server environment. Ubuntu is for the high-velocity developer who needs agility over absolute long-term predictability.
Okay, now that we've established that native Linux and Ubuntu in particular offers better architecture and a great desktop experience, let's get to the main event, the AI workflow battleground. Native Linux versus Microsoft's hybrid defense, WSL2.
This is where the rubber meets the road. Ubuntu is, without question, the undisputed global standard for AI infrastructure. Every major research paper, every Docker container, every Kubernetes deployment, it's all built on Linux and by 86.
And we talked about container efficiency. Remind us how that gives it a measurable performance lead.
The Nvidia Container Toolkit on Linux uses native kernel mechanisms, groups, and namespaces for basically zero overhead GPU pass-through. There is no virtualization penalty.
And what does that mean in the real world? Quantify that advantage.
Benchmarks consistently show native Ubuntu outperforming Windows 11 by about 5 to 8% in generative AI workloads.
Tokens per second, iterations per second?
Exactly. And for an enterprise running a training job for weeks, that single-digit percentage gain translates directly into huge cost savings on electricity and cloud compute.
And memory efficiency plays a big role here too.
A critical role, Linux is just leaner. It's not managing WDDM's complexity or the general Windows desktop overhead. That leaves more VRAM available for the AI model itself.
And every megabyte of VRAM is a strategic asset when you're trying to squeeze in a big LLM.
For sure. And, the ultimate proof is the Azure paradox.
Microsoft's own high-end cloud AI infrastructure, the big NV and ND series VMs.
They all overwhelmingly rely on optimized Ubuntu HPC images.
It's an implicit acknowledgement that for high-end, scalable compute, Linux is the necessary OS.
It is. Microsoft knew developers were leaving for this native performance, so their master strategy was to stop them from leaving the Windows desktop entirely. Enter WSL2.
The Windows subsystem for Linux version 2, a triumph of engineering.
It really is. It runs a real Linux kernel and a lightweight optimized VM. The strategy is simple. Give developers the Linux environment they need without forcing them to abandon the Windows desktop they know.
And the centerpiece is GPU paravirtualization, which projects a virtual GPU into the Linux guest.
It's an incredibly complex handshake, translating Linux GPU commands into WDDM calls on the Windows side. But it's not free. There's a cost.
What's the cost?
Latency. The cost is virtualization overhead, which shows up as latency and serialization lag, especially in I/O-heavy tasks.
So for a long, sustained compute job, like a single PyTorch training run, WSL2 is almost native speed.
Yeah, within 1%. But for tasks with tons of tiny kernel launches, like loading huge datasets or heavy file system access, that virtualization overhead in the communication channel degrades throughput measurably.
That I/O latency is the tax you pay for the convenience.
It is. But the workflow integration is its masterstroke, the reason it's winning.
The VS Code remote WSL extension, it decouples the editor on the Windows side from the execution on the Linux side.
That decoupling is brilliant. Developers get to use the polished, IT-compliant Windows UI while transparently running their actual code on a native Linux stack in the background.
It lets Microsoft keep the user interface monopoly even while they cede the compute monopoly to Linux.
It's a highly effective Trojan Horse strategy.
Okay, so we've covered the tech, the workflow. The compute difference is marginal for most. But for Linux to really go mainstream, it has to get over these huge, non-technical structural walls built by proprietary software vendors.
These walls are the biggest thing holding Linux back today. It's not about kernel drivers anymore. It's about policy and business decisions.
And the gaming barrier is the most ironic, right? Because Valve's Proton compatibility layer is a technical marvel. It's erased the performance gap for thousands of games.
The work they've done translating DirectX to Vulkan is phenomenal. For standard rendering, you're looking at near-native performance.
But there's still a catch.
There is. A technical tax remains for the most advanced features. There's about an 18 to 20% performance penalty for ray tracing, because translating those calls is just computationally expensive.
But that's not the real brick wall. The real failure is corporate policy around kernel-level anti-cheat.
This is an irreconcilable conflict. It's a clash of security philosophies.
Systems like Riot's Vanguard or Activision's Ricochet.
All right. On Windows, they operate at ring zero. They require deep, intrusive access to system memory and hardware states to detect cheats.
And the Linux kernel's entire security model says, absolutely not.
The kernel community views granting that kind of deep, unchecked access to a proprietary, unsigned binary as an unacceptable security risk. It's giving God-level privileges to a black box.
So it's a policy wall, not a technical one.
And the consequence is immediate eviction. If you try to play Valorant on Linux, Vanguard's requirement means you're just banned from playing, period.
And that proprietary wall extends directly into the professional software world. Adobe, high-end CAD.
The problem here is zero native Linux support for the Adobe Creative Cloud, Photoshop, Premiere Pro. They rely so heavily on Windows-specific APIs, especially proprietary color pipelines and registry hooks, that compatibility layers like Wine just can't keep up.
So even if you get it to launch, you can't trust it for professional work where color accuracy or stability is everything.
It's a non-starter for any serious studio. Professionals are forced into these clunky, resource-heavy workarounds, like streaming a Windows VM desktop to their Linux machine.
Which completely defeats the purpose of running a lean, native Linux setup.
Completely. And it's the same story in the engineering and CAD world. SolidWorks, AutoCAD, they're non-functional on Linux. They're too deeply hooked into Windows and DirectX.
So the only option for a Linux engineer is to abandon the local desktop entirely.
And move to cloud-native CAD like Onshape, which runs in a browser, or use desktop streaming services. But that introduces latency and connectivity dependencies.
So the barriers are clear. It's corporate policy and platform lock-in, not any technical failure of Linux itself.
Which brings us to the third path. The great architectural schism, Apple Silicon. This is the platform that just said no to the modular standard and decided to fight on a completely different battlefield.
A battlefield defined entirely by memory capacity.
And this split, it wasn't an overnight decision. It was driven by some pretty deep historical acrimony. You can trace Apple's move away from Nvidia directly back to the Bumpgate incident around 2008.
Right, where faulty Nvidia GPUs were causing widespread hardware failures in MacBook Pros. A total disaster for Apple's reputation.
It was. And Nvidia's handling of it, their perceived refusal to take full responsibility, it destroyed Apple's trust in them as a supply chain partner.
Apple needs total control over core components. That's their whole philosophy.
And relying on a partner who couldn't guarantee quality was an unacceptable strategic risk. That mistrust led directly to them dropping NVIDIA support in the macOS Mojave era and accelerating the development of their own silicon.
The M-series chips and the proprietary unified memory architecture, UMA.
And that UMA architecture is now the single most critical differentiator in local generative AI today. It solves the capacity problem that fundamentally breaks x86 systems.
Okay, let's revisit that VRAM bottleneck. Even the top-of-the-line RTX 4090 is capped at 24 gigabytes of VRAM. Why is that limit so catastrophic?
That 24 gig cap is a hard, physical, and often strategic barrier. To run a really large model, say a 70 billion parameter LLM, you need 35 to 40 gigs of memory, even when it's quantized.
So if you try to run that on a 24 gig card,
the model layers that don't fit in VRAM have to be constantly swapped to the much slower system RAM.
Across that agonizingly slow PCIe bus.
Exactly. And performance it crashes. It goes from a usable 50 tokens per second down to maybe 2 to 5. The PC architecture, regardless of OS, fails completely.
And Apple's unified memory is the direct solution to this problem.
It is. UMA puts the CPU, GPU, and the neural engine all on a single chip, sharing one massive pool of memory. A Mac Studio can have up to 192 gigabytes of this unified memory.
So there's no more copying. The data is just there, instantly accessible to both the CPU and GPU.
The copy tax drops to near zero. Now there is a trade-off. NVIDIA still wins the bandwidth crown for pure velocity. The 4090 has higher memory bandwidth.
So NVIDIA wins on velocity for smaller models that fit in that 24 gigs?
But Apple wins decisively on capacity.
Because it can actually run that massive 70B model. It's slower, maybe 8 to 12 tokens per second, but it runs. The PC is functionally broken.
This capacity advantage has strategically positioned the high-end Mac as the premier local AI server for researchers and hybrid developers. It's the only consumer platform where you can meaningfully experiment with these huge models locally.
And on the software side, it's CUDA on the PC side versus Apple's new MLX framework.
Right. CUDA is still the lingua franca for cloud training. But MLX, which Apple released late last year, is specifically optimized for UMA. It's capacity-aware, it's researcher-friendly.
So we're seeing a new hybrid workflow emerge.
We are. Developers are using the Mac's massive local capacity with MLX for prototyping and testing these huge models.
And then they SSH into an Ubuntu server, either local or in the cloud, for the heavy, scalable training using CUDA's velocity and mature ecosystem.
The bifurcation is complete. The choice for a serious AI developer is no longer just Mac versus PC. It's a strategic choice between maximizing capacity on Apple and maximizing velocity on Linux.
Okay, we have reached the end of our deep technical dive. It's time to translate all of this into the most fundamental decision for our listener. That budget-conscious AI developer who has bet their life savings on this dream.
And we have to ground this in cold, hard numbers based on real-world analyses comparing Ubuntu AI workstations to Apple Silicon.
Yeah.
And, full disclosure, we are both heavily biased towards the open ecosystem.
Right.
I use Debian for my heavy dev work, and for this podcast, for compliance and convenience, we're actually testing WSL2 on Windows 11.
But bias aside, the numbers and the engineering goals have to speak for themselves. So let's compare the two paths. The Ubuntu workstation, which is the velocity and parity choice, versus the Apple Silicon Mac, the capacity and efficiency choice.
The Ubuntu workstation is built around a strategic asset, a used 24GB RTX 3090. This card is a market anomaly.
Because new consumer cards artificially restrict VRAM.
Exactly. So the 3090's VRAM capacity makes it more valuable for LLM work than newer, technically faster cards with less memory.
What's the rough build cost for something like that today?
If you get a used 3090, a good amount of DDR5 RAM, and a decent CPU, you can put together a really powerful machine for around, say, $2,100.
And what does that $2,000 buy you in performance?
Superior velocity. For common models like Llama 3.8b, you're looking at around 100 tokens per second. And crucially, it offers perfect one-to-one dev-prod parity with the cloud. Linux by 86 CUDA. No cross-architecture bugs.
What's the deficit?
It fails completely on the big 70B models. Less than 1 token per second. The energy cost is also a hidden killer. That machine can add almost $1,500 to your electric bill over 5 years. And the resale value is low, maybe 30%.
Okay, now for the challenger. An Apple MacBook Pro with an M3 Max chip and 48 gigs of unified memory.
The initial buy cost is much higher. Around $3,300. It's a big upfront investment.
But it's the capacity king.
Absolutely. It runs those 70B models that break the PC at a usable 8 to 12 tokens per second. The energy cost is incredibly low, maybe $165 over 5 years. And Apple hardware holds its value exceptionally well. You can often get 60% back after 3 years.
So it's slower on small models, but it actually works on the huge ones. What's its core deficit for a professional cloud engineer?
The deployment friction. The ARM64 architecture and MLX create a mismatch with the by86 CUDA cloud standard.
Right.
You get those frustrating, works on my machine but breaks in production bugs.
Okay, let's bring it home. Total cost of ownership over 3 years, factoring in resale and energy costs.
And here's the surprise. The high resale value and low energy cost of the Mac narrow the TCO gap significantly.
Right.
The net cost of the PC over 3 years is about $1,350. The net cost of the Mac is about $1,300.
Wow, they're practically the same.
So if TCO is comparable, the decision comes down purely to the engineering objective of the developer.
The final verdict.
The Ubuntu workstation wins decisively for the professional cloud-native engineer who prioritizes training velocity and deployment parity. If your job is pushing code to by86 cloud servers, this is your perfect mirror. The MacBook Pro is superior for the mobile or hybrid developer who prioritizes local capacity and energy efficiency, using the cloud only for the heaviest training jobs.
And that wraps our deep dive into the AI desktop wars. We want to remind you, as always, that the content we create here is fully open source. We use sources shared all over the web to learn and frame our analysis for the show.
And we invite you, our listeners, to share more sources in the comments if you feel our analysis is even a tiny bit off base. The goal is always a symbiosis of artificial and natural intelligence.
And yes, we are always looking for human collaborators who could review and critique our content before we publish. So please drop a comment if you want to help us on this mission.
Our discussion today really highlighted that irreconcilable conflict between the open philosophy of Linux and the proprietary policy walls built by vendors in gaming and pro software.
Those walls are the only things stopping Linux from dominating the mainstream desktop.
So, let's leave you with a final provocative thought building on that. Will cloud-native solutions, like browser-based CAD or game streaming services, render the local desktop OS decision moot in the next few years?
Because if those policy walls are just bypassed by the browser, then developers are free to choose their OS purely based on the chip architecture that maximizes their AI workflow.
The fight shifts entirely to the silicon, capacity on Apple or velocity on Linux.
It changes everything. As always, keep searching, keep the quest on.